let's multiply everything times j omega Lr. So if we multiply everything times that, then I can cancel it. I can cancel it here and cancel it here as long as I square it there, right? And now let's rewrite again. So we got 1 plus R2 over R1. We've got j omega Lr. All right, so we need to expand that square. So I've got R squared plus 2 j omega Lr plus j squared omega squared L squared plus j omega Lr. Right? Okay, well this is a real number. This is a real number, so this has to be a real number too. But we've got j in the numerator, so the j needs to cancel out with the j in the denominator for this to be a real number. So all this has to be real, which means that this term needs to cancel with these two terms right here, which are both imaginary. These two terms are real. So the two real terms, they need to add up to 0 so that we get a purely imaginary denominator. Our j squared is minus 1. And this gives me the frequency of oscillation. Omega equals minus R over L, right? Omega equals R over L. Yeah. And then what's left will tell us the requirement on the gain. So 1 plus R2 over R1 needs to be I got 3 down there, right? So the gain the amplifier has to have a gain of at least 3 in steady state, right? If I were to build it, I would want it to have a higher gain than that so it gets started. So that one works. Part B is not going to work. I can tell from inspection because there is insufficient phase shift. You see, if it's an ideal inductor, there's no current. There's no current through it. That means the voltage here equals the voltage here. There's no omega anywhere in the circuit, right? If there's no current through an inductor, it doesn't do anything. So you might say, well, what happens if the amplifier is not ideal, right? And then we actually get current through the inductor. Well, then we'll have a j omega L here, but no way to separate the j from the omega because I need at least 2 elements. And you see, that's where the squared came from, the fact that I had 2 inductors. Besides, you can think of it another way. This is something like a low-pass filter around that loop. A low-pass filter, you can't get a frequency, right? It just sends the frequency lower and lower and lower until it gets down to nothing. So you'll get a big 0 out of this one. Let's look at C. C is very similar to A. Okay, so for C, we've got a capacitor C and an inductor here, and then a resistor R. So the gain through the amplifier is still the same right here. And again, I can use voltage division here to find the gain through this filter. I know it's going to work, right? This is a bandpass filter. Should be fine. I'll multiply everything times j omega c to kind of clean up the fraction. So I'll multiply that times j omega c. So we got j omega rc plus 1. Okay, now we got minus from the j squared, so omega squared lc. lc, yeah. All right. And this one's even easier to work than A because we can already see what's going to happen. This is real, the imaginary part has to cancel. The only way for that cancellation to happen is if that is 0, right? So the frequency is square root of 1 over LC, which is exactly where you expect it to be. That's the center of the pass band from that two-pole bandpass filter, right? It all makes sense. As for the requirement of the gain, it's clear that the gain has to be at least 1 through the amplifier. That should be very easy to achieve, right, with the op-amp circuit. So this one would work, no problem. Does anyone have any questions on any of these circuits before I erase? Because I'll need the whole board space to work the last one. I'll give you a minute. Let's see if you're still copying it down. Maybe before I work the lesson, let me give you another example. I'll give you one more example. Because I really want to work through an example that won't work, but without doing it by inspection. Okay. Maybe that would be also instructive. Let me rework this problem, but with a very, very small change. Let's take out the inductor, right? And then I'll show you that it won't work mathematically. What's going to change? So without the inductor, you see this term is gone. This term is gone. Not possible, right? Not possible. I can't cancel it because, for that to cancel, I have to have 1 equals 0. Not going to work. It's clear. The only way for it to work, right, is if you have all the voltages at 0. Yeah, then it all works. All the voltages at 0, then 0 through the amplifier, 0 through the filter. That steady state 0 is the only solution. Okay, now this circuit is more complicated. This one. It won't take us too long to work though. this circuit is not easy to see right away that it's going to work, right? It turns out to work, and it's actually a very special circuit. I'll show you why it's special later, but in fact, the main oscillation loop is this one right down here. And I can tell that it's going to work for the following reason. We've got a positive feedback loop down here, and you see one capacitor is in series, and the other one is in shunt, right? So one shifts the phase forward, and then one's going to shift the phase back. And so this is going to work. It's almost like a Wayne-Bridge oscillator, but it's special, and I'll show you why it's special later. I don't have any special way to solve this one like I had with the others, right? So to solve this one, we'll use a more traditional approach. I'll just label all the voltages and currents, and we'll see what pops out of the equations. So let's label this VO. Let's label this Vx. Let's label this over here Vy. Just kind of randomly, yeah? Now let's label these currents. Let's label this I1. Let's label this I2. And let's label this I3. Now, I've got 6 variables up here. All of them are unknown. I need at least 6 independent equations in order to eliminate all of them. Right? So now that's our goal, is then to start writing equations. So first thing we'll do is let's kind of extend these labels a little bit, because, for example, this is at 0 volts here, and as long as our gain is not infinite or minus infinity, that also ought to be 0 volts there. I3 is moving along that line. It all goes down through the capacitor, if this is a good amplifier. Vx is the voltage that sits right here from over there, so that if it's a good amplifier, this voltage should also be Vx, right? Now let's write some equations. So first of all, I can see kind of a standard configuration inverting amplifier right there, and I know the gain for that one. The gain is Vy over Vx equals minus R1 over R2, right? So that's one equation. I'm kind of working my way around the loop. Now for the second equation, let's look at this one. You see all the current that passes through resistor R1, again, has to pass through resistor R1, right? Because none of it can branch down there through the amplifier. So the current through that first resistor, that's Vy minus Vx over R1, right? I use Ohm's law, V over R. The current through that second resistor, R1, that's Vx minus Vo over R1. R1s are going to cancel. These equations just tell us that Vx sits halfway between Vy and Vo. Okay, now let's apply Ohm's law for this lower branch down here. So my I1 is flowing from right to left, so Vo minus Vx, that's that way, should equal, V equals IR, V equals I1 times, I need the whole impedance, R1 plus 1 over j omega c. Now, I'm going to look at this branch right here. Apply Ohm's law. So Vx, I got 0 on the other side, equals I to R2, right? V equals I to R. And we also have this branch right here. So Vx equals I3 times the impedance of that capacitor. And finally, for the the sixth equation, I'm going to use the Kirchhoff current law at this node. Those currents all have to sum up to 0. So we've got in equals out. So we've got current I1 coming in, and we've got I2 and I3 coming out. So there's all 6 equations. They're all independent. I don't want to go through all the algebra. I'm sure you'll believe me that they can be eliminated, right? Let's not do that. I'll show you the last step, though. So here's what we get after about a half a page worth of work. Here's what's left after all the variables are eliminated. One equation left. And, just like before, I would, one way to work this problem would be to kind of expand it out and then set the real equals real, imaginary equals imaginary. You get 2 equations. So that's what we can do here. We can set the imaginary parts equal to each other. In this case, it's very special because the imaginary parts are already equal to each other, right? And that's unusual. In the circuits that I solved before, the imaginary parts were not equal to each other. They're only equal to each other for certain values of the gain, right? For this particular oscillator, they're already equal, so no problem, right? Those cancel. So I'm just left with, let me move the 1 over, and j squared is minus 1. And I now have the frequency. So it's 1 over that, right? So I now have the frequency of oscillation, and that's the only answer that comes out. And I'll tell you why this is a very special oscillator. With the Weinbridge oscillator, like the one that you build in the lab, to change the frequency, you've got to adjust 2 different resistors, not 1. On the other hand, for this one, you see the equation depends on both resistors, but R2 only shows up once in the circuit. So if you make this one adjustable, you can change the frequency without screwing up the gain. And you don't have to adjust 2 resistors, just 1. So it's like a Weinbridge oscillator with kind of an automatic gain control built into it. So you can adjust R2 all you want, and the imaginary parts still cancel out. So this oscillator works really well. If I were going to build it, I would probably make this one a little bit bigger than R1 because you need a little bit higher gain in order to get it started. I'll join you all in the lab tomorrow, if I can.